What if the secret to making a computer like 1,000 times faster and significantly more energy efficient is actually teaching it how to be deliberately mathematically wrong?
I mean, it sounds completely counterintuitive, right? But yeah, that is exactly the kind of paradigm shift we are getting into today.
Exactly. So today we are taking you into the architecture of this massive, just meticulously structured slide deck repository. It was created by a user known as Look036 back in 2026.
Yeah, hosted at look036.github.io.
Right, that's the one. And it is a staggering collection. We're talking over 100 presentations spread across 18 different directories, but we aren't just looking at a standard tutorial site today.
Oh, definitely not. It's so much more than that.
Yeah, we're going to explore this complete unbroken journey, like starting from the most abstract, mind bending mathematics and taking that straight down to the physical silicon of microchips, and then finally getting into the intensely rigorous software that, binds the whole thing together.
And that synthesis, I mean, that is what makes this source uniquely valuable because we often treat theoretical algorithms or, hardware manufacturing and software engineering as these totally isolated silos.
Right, like they don't talk to each other.
Exactly. But this repository completely dismantles those walls. It shows how the physical constraints of an actual integrated circuit directly dictate the math models we have to choose.
Wow.
And then how those models, in turn, sort of force us to adopt very specific memory safe programming paradigms, really just to keep the entire system from collapsing under its own complexity.
So, our mission on this deep dive is basically to serve as your personal Sherpa through this incredibly dense intellectual landscape.
A very necessary Sherpa, honestly.
Yeah, we want to unpack the core mechanics hiding in these slide decks. So, you know exactly how to leverage these tools without getting totally paralyzed by information overload, because it is a lot.
It is a massive amount of data.
It's kind of like finding a map to this hidden underground library. Like, the first wing is purely abstract math. The second wing takes that math and turns it into physical microchips. And the third wing is this intense coding boot camp that makes it all actually run.
I love that analogy. It's very accurate.
Thanks. So let's start at that absolute foundation, right? The mathematical blueprints. The repository dives really heavily into convex optimization and n-sphere sampling. And the author, they don't hold back. They plunge straight into linear matrix inequalities, or LMIs, and this thing called the ellipsoid method.
Yeah, LMIs are essentially the heavy lifters of optimization. So imagine engineers designing a system with, I don't know, millions of variables.
Like the power distribution network across a whole microchip.
Exactly. They face countless overlapping constraints. So convex optimization is about finding the absolute lowest point in this sort of multidimensional mathematical bowl.
Okay, multidimensional bowl.
Right. And because the space is convex, you know for a fact that any local minimum you find is the global minimum. It's the absolute best answer.
Got it. And the ellipsoid method.
So the ellipsoid method and LMI formulations, they allow an algorithm to draw an imaginary, shrinking, multidimensional shape like an ellipsoid around that lowest point.
Yeah.
And it literally cuts the search space in half with every single iteration.
Wow, just slicing it down.
Yep. The repository even documents a dedicated Python package created just for this called illalgo.
Okay, so that concept of searching through multidimensional space, that transitions perfectly into the n-sphere directory because the author explores generating points on spheres in multiple dimensions.
Yeah, things get pretty wild there.
Right, like the unit 2 sphere in 3D space or the 3 sphere in 4D space. And to do this, the source details what are called low discrepancy sequences, specifically the van der Corput sequence in base B.
Oh, that is a fantastic mathematical concept.
It is, but the text lays out this really complex van der Corput radical inverse equation, where the sequence value at n is calculated by taking the sum of the digits of n in base B and then multiplying that by b to the power of negative I minus 1.
I know, when you just hear the math spoken out loud, it sounds like absolute nonsense.
It really does. How do we visualize that?
Okay, to visualize the mechanics of that equation, just imagine taking a normal sequence of integers. You write them in a specific numerical base-like binary or base 3,
Okay.
and then you literally reflect those digits across the decimal points like a mirror. So a very large integer suddenly becomes a highly specific, very small fraction.
So if I'm trying to translate this out of pure math, is using a low discrepancy sequence like van der Corput basically like trying to perfectly space out seeds in a garden?
How do you mean?
Like, so no spot is too crowded or too barren, because if you just throw the seeds randomly, you inevitably get these massive clumps and then wide open gaps where nothing grows. But this mathematical mirroring trick guarantees the seeds, or, well, the data points, fill the entire geometric space with pristine uniformity.
Yes. The garden visualization perfectly captures the mechanism, and hardware engineers completely rely on this uniformity for things like quasi Monte Carlo methods and hardware test generation.
Right, because testing hardware is a massive undertaking.
Absolutely. If you are testing a newly designed microchip,
Okay.
it has billions of possible logic states. You literally cannot test every single combination.
It would take forever.
Exactly. And standard random sampling is too clumpy, like your garden seeds. You might test the exact same logic gate cluster repeatedly while totally missing a catastrophic flaw sitting right there in a statistical gap.
Oh, wow. So you need that perfectly even spread.
Right. The van der Corput sequence generates a highly uniform set of test vectors that effectively sweeps the entire multidimensional design space.
Okay, that makes sense. And the source also connects this pure geometry to physical hardware implementations. It specifically mentions Cordic
Ah, yeah, Cordic.
because multiplication operations take up a massive amount of physical area on a silicon wafer, right? So I assume Cordic is a way to calculate complex geometry like sine and cosine without actually using physical hardware multipliers.
You nailed it. The mechanism behind Cordic, which stands for Coordinate Rotation Digital Computer Algorithm, it's incredibly elegant for that exact reason. Instead of multiplying, it computes trigonometric functions using literally nothing but bitwise shifts and simple additions.
Just shifts and additions. How?
Well, in binary, shifting a sequence of numbers one position to the left effectively multiplies the whole thing by 2, and shifting it right divides it by 2.
Oh, right, because it's base 2.
Exactly. So by repeatedly rotating the phase of a signal using these pre-calculated bit shifts, Cordic arrives at incredibly precise trigonometric values.
That's wild.
Yeah, it sacrifices just a tiny amount of clock cycles to save a massive, massive amount of physical silicon real estate.
Which is huge because silicon real estate is expensive. And that brings us to the reality of forcing physical silicon and copper wire to actually obey these mathematical rules.
The fun part?
Yeah. The repository dedicates a ton of space to VLSI, very large scale integration and hardware design. This is where the abstract blueprints hit physical reality. Under the FISDs directory, the author details circuit partitioning using the FM algorithm and global placement with min-max fairness.
Right. So the fiducia Mathiases, or FM algorithm, that addresses the physical bottleneck of wiring.
Because there's a lot of wiring.
Billions of transistors worth. So you have to partition them into separate blocks on the chip. The FM algorithm strategically moves individual nodes like transistors or logic gates between different partitions to minimize the number of wires that have to actually cross the boundary between them.
Got it. So keeping related things close together.
Exactly, which dramatically reduces delay and power consumption.
And timing is everything here because the source digs into the DME algorithm deferred merge embedding specifically for routing clock trees. And the clock signal, I mean, that is the heartbeat of the microchip, right? Every single component has to receive that pulse simultaneously.
Yes, and that is a massive physical challenge. If the copper wire carrying the clock signal to the top left of the processor is physically longer than the wire going to the bottom right.
It arrives late.
Exactly.
Yeah.
It arrives a fraction of the picosecond late. And that timing failure is called clock skew. It'll crash the whole chip.
Wow.
So the DME algorithm works backward. It starts from the logic gates and works back to the central clock source, mathematically calculating these incredibly rigorous merging points to route the wires.
Just perfect symmetry.
Yeah, it guarantees that the wire length and therefore the signal delay is perfectly identical across the entire physical topography of the chip.
That is insane precision. And the physical constraints get even more intense when we look at the design for manufacturability or DFM directories.
Oh yeah, because making these things is a nightmare.
Right, because at modern microscopic scales, you can't just draw a circuit diagram and expect a laser to print it onto silicon. The features we are trying to print are actually smaller than the wavelength of the light being used to print them.
Which is just wild to think about.
It really is, and it means the light diffracts and blurs. You won't print a clean line.
Right, the manufacturing process relies on photolithography. And overcoming that diffraction requires what we call phase shifting masks, or PSMs.
Okay, how do those work?
Well, engineers intentionally alter the physical thickness of the glass mask that the light shines through. By doing this, they literally shift the phase of the light wave by 180 degrees.
Okay.
So when the shifted wave meets an unshifted wave on the silicon surface, they destructively interfere. They cancel each other out to create a perfectly crisp, dark line that separates two tiny microscopic wires.
That is basically magic. But the text frame's calculating exactly which parts of the mask to shift as an NP complete problem.
It is.
And to solve it, the author uses phase conflict graphs and something called Hadlock's algorithm.
Yeah, so NP completeness basically means the problem scales exponentially. There is no known fast mathematical shortcut to find the absolute perfect solution.
It just takes too much computing power.
Way too much. So Hadlock's algorithm tackles this by finding the maximum bipartite subgraph.
Okay, in English.
It essentially looks at this incredibly complex web of adjacent wires where the light might bleed over and ruin the chip. And it calculates the most efficient way to assign those 180-degree phase shifts to minimize conflicts. It makes the chip actually manufacturable without needing infinite time to compute the mask.
Okay, and this leads directly back to my opening question for the deep dive. Right after the author details all this insane, precision-like, perfect clock skew, light bending, lithography masks, we hit the AXI directory.
Approximate computing.
Yes. Suddenly, there is an entire section dedicated to, quote, approximate multipliers and multiplierless FIR design. Like, wait, we've spent decades trying to make computers flawless exact calculators. Why would there be an entire section dedicated to making them wrong?
I know, it feels like a total betrayal of everything we just talked about.
Yeah.
But the shift toward approximate computing is driven by a brutal physical reality. Absolute precision requires massive amounts of energy and time. In traditional computing, exactness is non-negotiable. But the repository heavily features coarse-grained reconfigurable architectures, or CGRAs, and hardware acceleration for neural networks.
Okay.
And in those specific domains, we can actually trade mathematical perfection for extreme efficiency.
So if I'm building, say, an image recognition neural network, the system inherently relies on aggregate probabilities anyway, not absolute binary logic.
Exactly.
So if a hardware multiplier gets the math right 99% of the time or gets it close enough, the tiny rounding error just blends into the statistical noise and the network still correctly identifies that a picture is of a cat.
Yep. And the underlying mechanism of that trade-off is profound. Think about a perfect 32-bit hardware multiplier. It requires thousands of interconnected logic gates. It generates significant heat and consumes a lot of power.
Obviously.
An approximate multiplier simply chops off the physical logic gates that are responsible for calculating the least significant bits.
Wait, they just remove them?
Literally. The hardware shrinks in physical size, uses a fraction of the power, and completes the calculation in significantly fewer clock cycles.
That is so smart. And the source pairs this with a concept called canonical signed digit representation, or CSD, through a package called Stigit. I looked at the math here and it's brilliant.
It's very cool.
Yeah, so in standard binary, the number 15 is 1111, right? That's 4 separate additions for the hardware to process.
Yep.
But CSD represents numbers by minimizing the non-zero digits. It recognizes that 15 is just 16 minus 1.
Right.
So it represents it as 1,000 with a negative 1 at the end. You achieve the exact same. That is incredible. We are using flawless multi-dimensional mathematics to optimize exactly how to build an imperfect, highly efficient physical calculator.
It's a beautifully closed loop.
It really is. But orchestrating billions of perfectly placed, light-bent, approximate transistors, that requires incredibly robust software tools. So the massive scope of this hardware engineering naturally forces us into the programming and network optimization topics in the repository.
Right. The author spends significant time outlining modern C++17 and C++20 paradigms, alongside some really complex graph theory in the Netoptum directory.
Because designing a microchip is basically a graph optimization problem.
At its core, yeah.
Yeah.
You have millions of nodes and edges representing transistors and wires. The repository details algorithms like negative cycle finding using the Bellman-Ford or Howard algorithms.
Now, why are negative cycles so dangerous in a chip's design?
Well, a negative cycle in a timing graph implies a loop where the total time delay is less than 0.
Less than 0.
Yeah. In physical terms, it implies a signal is arriving at a component before it was even sent.
Which is literally a physical impossibility.
Exactly. It usually indicates a fatal flaw in the logical timing constraints of the chip's design. The Bellman-Ford algorithm systematically sweeps through the entire graph, relaxing the edges to calculate the shortest paths. And if it can still find a shorter path after checking every single node, it flags a negative cycle, allowing engineers to fix that timing violation before it's manufactured.
Okay, that makes total sense. The source also drops a reference to the Christofides algorithm for the metric traveling salesperson problem, which is a classic routing dilemma.
Oh, yeah, the TSP.
Right. Instead of brute forcing every possible path to find the absolute shortest one, Christofides guarantees a route that is at most 1.5 times longer than the absolute perfect path.
Right, the 32 approximation.
Yeah. It does this by creating a minimum spanning tree, which is the shortest possible web connecting all points, and then specifically identifying the points with an odd number of connections. Then it uses a perfect matching algorithm to pair them up. It's essentially a mathematically guaranteed shortcut.
It is a phenomenal example of approximation algorithms saving computational time, just like in the hardware.
Yeah.
But, managing algorithms of this complexity, especially legacy C++ tools like the fizz package mentioned in the text, it introduces immense software instability.
Oh, I'm sure.
Which brings us to a major central narrative running through the Rust by Examples directory. And that's the concerted effort to migrate these massive C++ and Python engineering packages over to Rust.
Yeah, the Rust migration. So the challenge with C++ in these massive EDA environments is memory management, right? Like one misplaced pointer when trying to calculate billions of light diffractions can create a massive memory leak or a catastrophic data race.
Absolutely.
So if coding in C++ is like driving a manual transmission race car where one wrong move blows the engine,
Right.
is migrating everything to Rust with its strict ownership and borrowing rules? Is that like installing an advanced AI safety system so the card literally won't let you crash?
The safety system analogy is highly accurate. In C++ plus E, multiple threads can try to write to the exact same memory address simultaneously.
Which causes a crash.
A crash that is virtually untraceable.
Yeah.
But Rust's borrow checker enforces these strict single writer or multiple reader rules at compile time. It fundamentally refuses to even compile the program if there is even a theoretical possibility of a memory conflict.
That is so strict.
It is, but it's necessary. The author explicitly highlights utilizing GPU-accelerated vertex cover algorithms in Rust using a crate called CUDARC. Writing concurrent GPU code is notoriously difficult, but Rust's strictness makes that concurrency fearless.
Wow. And it looks like the author isn't just abandoning other languages, though.
No, not at all. By using core packages like digraphs, CKT, TMPy, and Progium, the author demonstrates a seamless cross-language workflow.
Using the right tool for the job.
Exactly. They advocate using Python for rapid prototyping and high-level graph logic, then C++ for integrating with decades of legacy hardware layout code. And finally, Rust for building memory-safe, hyper-concurrent algorithms on the GPU. It really trains the reader to use the specific language best suited for the specific hardware bottleneck.
Okay, so for the listener who is sitting there ready to pull down this code, implement the FM algorithm, or build an approximate multiplier, we need to discuss the actual architecture of luck036.github.io.
Yeah, the site itself is a project.
Right. The repository isn't just teaching these workflows, it is actively built on top of them. The site is hosted entirely on GitHub Pages, utilizing a JavaScript engine called remark.js to render markdown files directly into HTML slides inside the browser.
And the author integrated KTeX for ultra-fast rendering of the heavy mathematical equations, like our van der Korp radical inverse we discussed, and mermaid.js, to dynamically generate the complex graph theory architecture diagrams.
It's super robust. And the slide files follow a really strict naming convention too, like -remark.html for self-contained slides and -slides.md for external source markdown.
It's an incredibly clean setup, utilizing a unified Nord theme across all the decks.
But, and this is a big but, the author leaves a very specific technical warning for anyone trying to download this repository and run it locally, say for a listener who wants to study offline on an airplane.
Right, the local file issue.
If you just download the code and double-click the standard index.html file on your hard drive, your browser will completely block the content from loading. Why does that happen?
So the failure mechanism there is Core's cross-origin resource sharing. It is a fundamental browser security protocol.
Okay.
Remark.js relies on a source URL script command to dynamically fetch those external .md markdown files and inject them into the HTML.
Right.
When you host the site on a web server, the server handles this request seamlessly. But when you are offline, your browser just sees one local file trying to quietly read another local file via the file protocol.
Oh, and to the browser, that looks exactly like a malicious script trying to silently scrape personal files off your hard drive.
Exactly. So it forcibly blocks the action, leaving you with just a blank screen.
So how do you fix it?
The author's solution to bypass the core S restriction is those -remark.html files. These files follow an inline pattern, meaning the raw markdown text is injected directly into the HTML file itself during the build process.
Ah, so it doesn't need to fetch anything.
Precisely. Because the HTML file isn't executing a script to call an external file, it bypasses the security check entirely, allowing the dynamic slides to load perfectly offline.
It is literally a masterclass in elegant functional design.
It really is.
As we pull back and look at the sheer scope of the ground we've covered in this deep dive, the interconnectedness of this repository is stunning.
It's a complete ecosystem.
Yeah. We started in the abstract mathematical heavens, using the van der Kortput sequence to uniformly distribute points across infinite dimensional geometry. Then we drag that pure math down to the physical constraints of silicon, routing millions of microscopic wires with the DME algorithm.
And calculating phase shifting masks with Hadlock's algorithm to literally bend light itself.
Bending light.
Yeah.
And then we challenged the entire dogma of perfect calculators by embracing canonical sign digits for approximate computing. And finally, we explored how to safely architect all of this using the rigorous memory safeguards of the Rust programming language.
The entire repository stands as absolute proof that modern hardware and software engineering can no longer exist in isolation. You just cannot push the boundaries of VLSI physical design without a deep understanding of convex optimization.
Right.
And you cannot implement those mathematical theories at scale without utilizing memory-safe concurrent programming languages. It's all connected.
It really is. Before we wrap up, though, I want to leave you, the listener, with a final thought to kind of chew on. Something that's been lingering for me since we discussed approximate computing.
Oh.
Yeah. We have spent half a century forcing physical silicon to behave with absolute flawless mathematical rigidity. But if the absolute cutting edge of hardware acceleration now relies on deliberately sacrificing that perfection to gain immense speed and energy efficiency, are we moving away from building rigid calculators?
That's an interesting point.
Right. Could the future of computer engineering be fundamentally biological, like mimicking the noisy, imprecise, but incredibly fast probabilistic approximations of our own human brains?
Wow. It is a profound paradigm shift to consider. I mean, by engineering our systems to embrace a small amount of mathematical noise, we might actually be taking the very first steps toward making hardware function more like biology.
It's a fascinating frontier, and we highly encourage you to explore this vast intellectual landscape yourself by checking out the slide decks at luck036.github.io. There are dozens of algorithms and workflows we didn't even have time to touch today.
There really are. It's well worth your time.
Thanks for joining us on this deep dive, and keep questioning the mechanics of the tech around you.